Detecting faults. Many systems need to automatically detect faulty nodes. For example, a load balancer needs to stop sending requests to a node that is dead, i.e. take it out of rotation. In a distributed database with single leader replication, if the leader fails, one of the followers needs to be promoted to be the new leader. See handling node outages on page 156. Unfortunately, the uncertainty about the network makes it difficult to tell whether a node is working or not. In some specific circumstances, you might get some feedback to explicitly tell you that something is not working, if you can reach the machine on which the node should be running. But no process is listening on the destination port, for example, because the process crashed. The operating system will helpfully close or refuse TCP connections by sending a RSD or FIN packet in reply. However, if the node crashed while it was handling your request, you have no way of knowing how much data was actually processed by the remote node. If a node process crashed or was killed by an administrator, but the node's operating system is still running, a script can notify other nodes about the crash so that another node can take over quickly without having to wait for a timeout to expire. For example, HBase does this. If you have access to the management interface of the network switches in your data center, you can query them to detect link failures at a hardware level. For example, if the remote machine is powered down. This option is ruled out if you're connecting via the internet, or if you're in a shared data center with no access to the switches themselves, or if you can't reach the management interface due to a network problem. If a router is sure that the IP address you're trying to connect to is unreachable, it may reply to you with an ICMP destination unreachable packet. However, the router doesn't have a magic failure detection capability. Either it is subject to the same limitations as other participants of the network. Rapid feedback about a remote node being down is useful, but you can't count on it. Even if TCP acknowledges that a packet was delivered, the application may have crashed before handling it. If you want to be sure that a request was successful, you need a positive response from the application itself. Conversely, if something has gone wrong, you may get an error response at some level of the stack, but in general you have to assume that you will get no response at all. You can retry a few times. TCP retries transparently, but you may also retry at the application level, wait for a timeout to elapse, and eventually declare the node dead if you don't hear back within the timeout. Timeouts and unbounded delays. If a timeout is the only sure way of detecting a fault, then how long should the timeout be? There is unfortunately no simple answer. A long timeout means a long wait until a node is declared dead, and during this time, users may have to wait or see error messages. A short timeout detects faults faster, but carries a higher risk of incorrectly declaring a node dead when in fact it has only suffered a temporary slowdown, for example due to a load spike on the node or the network. Prematurely declaring a node dead is problematic if the node is actually alive and in the middle of performing some action, for example, sending an email, and another node takes over. The action may end up being performed twice. We will discuss this issue in more detail in Knowledge, Truth, and Lies on page 300, and in chapters 9 and 11. When a node is declared dead, its responsibilities need to be transferred to other nodes, which places additional load on other nodes and the network. If the system is already struggling with high load, declaring nodes dead prematurely can make the problem worse. In particular, it could happen that the node actually wasn't dead but only slow to respond due to overload. Transferring its load to other nodes can cause a cascading failure. In the extreme case, all nodes declare each other dead, and everything stops working. Imagine a fictitious system with a network that guaranteed a maximum delay for packets. Every packet is either delivered within some time d, or it is lost, but delivery never takes longer than d. Furthermore, assume that you can guarantee that a non-failed node always handles a request within some time r. In this case, you could guarantee that every successful request receives a response within time 2d plus r, and if you don't receive a response within that time, you know that either the network or the remote node is not working. If this was true, 2d plus r would be a reasonable timeout to use. Unfortunately, most systems we work with have neither of those guarantees. Asynchronous networks have unbounded delays, that is, they try to deliver packets as quickly as possible, but there is no upper limit on the time it may take for a packet to arrive, and most server implementations cannot guarantee that they can handle requests within some maximum time. See response time guarantees on page 298. For failure detection, it's not sufficient for the system to be fast most of the time. If your timeout is low, it only takes a transient spike in round-trip times to throw the system off balance. When driving a car, Travel times on road networks often vary most due to traffic congestion. Similarly, the variability of packet delays on computer networks is most often due to queuing. If several different nodes simultaneously try to send packets to the same destination, the network switch must queue them up and feed them into the destination network link one by one as illustrated in Figure 8-2. On a busy network link, a packet may have to wait a while until it can get a slot. This is called network congestion. If there is so much incoming data that the switch queue fills up, the packet is dropped, so it needs to be resent even though the network is functioning fine. When a packet reaches the destination machine, if all CPU cores are currently busy, the incoming request from the network is queued by the operating system until the application is ready to handle it. Depending on the load on the machine, this may take an arbitrary length of time. In virtualized environments, a running operating system is often paused for tens of milliseconds, while another virtual machine uses a CPU core. During this time, the VM cannot consume any data from the network, so the incoming data is queued buffered by the virtual machine monitor, further increasing the variability of network delays. TCP performs flow control, also known as congestion avoidance or backpressure, in which a node limits its own rate of sending in order to avoid overloading a network link or the receiving node. This means additional queuing at the sender before the data even enters the network. Figure 8-2. If several machines send network traffic to the same destination, its switch queue can fill up. Here, port 1, 2, and 4 are all trying to send packets to port 3. Moreover, TCP considers a packet to be lost if it is not acknowledged within some timeout, which is calculated from observed round-trip times, and lost packets are automatically retransmitted. Although the application does not see the packet loss and retransmission, it does see the resulting delay waiting for the timeout to expire, and then waiting for the retransmitted packet to be acknowledged. TCP versus UDP. Some latency-sensitive applications, such as video conferencing and voice over IP/VoIP, use UDP rather than TCP. It's a trade-off between reliability and variability of delays. As UDP does not perform flow control and does not retransmit lost packets, it avoids some of the reasons for variable network delays, although it is still susceptible to switch queues and scheduling delays. UDP is a good choice in situations where delayed data is worthless. For example, in a VoIP phone call, there probably isn't enough time to retransmit a lost packet before its data is due to be played over the loudspeakers. In this case, there's no point in retransmitting the packet. The application must instead fill the missing packet's time slot with silence, causing a brief interruption in the sound and move on in the stream. The retry happens at the human layer instead. Could you repeat that, please? The sound just cut out for a moment. All of these factors contribute to the variability of network delays. Queuing delays have an especially wide range when a system is close to its maximum capacity. A system with plenty of spare capacity can easily drain queues, whereas in a highly utilized system, long queues can build up very quickly. In public clouds and multi-tenant data centers, resources are shared among many customers. The network links and switches, and even each machine's network interface and CPUs when running on virtual machines, are shared. Batch workloads such as MapReduce C Chapter 10 can easily saturate network links. As you have no control over or insight into other customers' usage of the shared resources, network delays can be highly variable. If someone near you, a noisy neighbor, is using a lot of resources, in such environments, you can only choose timeouts experimentally. Measure the distribution of network round-trip times over an extended period, and over many machines, to determine the expected variability of delays. Then, taking into account your application's characteristics, you can determine an appropriate trade-off between failure detection delay and risk of premature timeouts. Even better, rather than using configured constant timeouts, systems can continually measure response times and their variability jitter, and automatically adjust timeouts according to the observed response time distribution. This can be done with a PHI accrual failure detector, which is used, for example, in Akka and Cassandra. TCP retransmission timeouts also work similarly. Synchronous versus asynchronous networks. Distributed systems would be a lot simpler if we could rely on the network to deliver packets with some fixed maximum delay and not to drop packets. Why can't we solve this at the hardware level and make the network reliable so that the software doesn't need to worry about it? To answer this question, it's interesting to compare data center networks to the traditional fixed-line telephone network, non-cellular, non-VoIP, which is extremely reliable. Delayed audio frames and dropped calls are very rare. A phone call requires a constantly low end-to-end latency and enough bandwidth to transfer the audio samples of your voice. Wouldn't it be nice to have similar reliability and predictability in computer networks? When you make a call over the telephone network, it establishes a circuit. A fixed, guaranteed amount of bandwidth is allocated for the call along the entire route between the two callers. This circuit remains in place until the call ends. For example, an instant network runs at a fixed rate of 4,000 frames per second. When a call is established, it is allocated 16 bits of space within each frame in each direction. Thus, for the duration of the call, each side is guaranteed to be able to send exactly 16 bits of audio data every 250 microseconds Roman 2, except perhaps for an occasional keep-alive packet. If TCP keep-alive is enabled Roman 3, Asynchronous Transfer Mode ATM was a competitor to Ethernet in the 1980s, but it didn't gain much adoption outside of telephone network core switches. It has nothing to do with automatic teller machines, also known as cache machines, despite sharing an acronym. Perhaps, in some parallel universe, the Internet is based on something like ATM. In that universe, Internet video calls are probably a lot more reliable than they are in ours, because they don't suffer from dropped and delayed packets. This kind of network is synchronous. Even as data passes through several routers, it does not suffer from queuing, because the 16 bits of space for the call have already been reserved in the next hop of the network. And because there is no queuing, the maximum end-to-end latency of the network is fixed. We call this a bounded delay. Can we not simply make network delays predictable? Note that a circuit in a telephone network is very different from a TCP connection. A circuit is a fixed amount of reserved bandwidth, which nobody else can use while the circuit is established, whereas the packets of a TCP connection opportunistically use whatever network bandwidth is available. You can give TCP a variable-sized block of data, for example an email or a web page, and it will try to transfer it in the shortest time possible. While a TCP connection is idle, it doesn't use any bandwidth. Roman 2 If data center networks and the Internet were circuit-switched networks, it would be possible to establish a guaranteed maximum round-trip time when a circuit was set up. However, they are not. Ethernet and IP are packet-switched protocols, which suffer from queuing and thus unbounded delays in the network. These protocols do not have the concept of a circuit. Why do data center networks and the Internet use packet switching? The answer is that they are optimized for bursty traffic. A circuit is good for an audio or video call, which needs to transfer a fairly constant number of bits per second for the duration of the call. On the other hand, requesting a web page, sending an email, or transferring a file doesn't have any particular bandwidth requirement. We just want it to complete as quickly as possible. If you wanted to transfer a file over a circuit, you would have to guess a bandwidth allocation. If you guess too low, the transfer is unnecessarily slow, leaving network capacity unused. If you guess too high, the circuit cannot be set up because the network cannot allow a circuit to be created if its bandwidth allocation cannot be guaranteed. Thus, using circuits for bursty data transfers wastes network capacity and makes transfers unnecessarily slow. By contrast, TCP dynamically adapts the rate of data transfer to the available network capacity. There have been some attempts to build hybrid networks that support both circuit switching and packet switching, such as ATM. Roman 3 InfiniBand has some similarities. It implements end-to-end flow control at the link layer, which reduces the need for queuing in the network, although it can still suffer from delays due to link congestion. With careful use of quality of service QoS, prioritization and scheduling of packets, and admission control rate limiting senders, it is possible to emulate circuit switching on packet networks or provide statistically bounded delay.